Hi everyone, my name's Kevin and today I'm going to be talking about the UAV I built as a capstone project for my embedded systems and my control systems courses. This presentation covers more of the embedded systems side, but if you're interested in the control systems development that I did for this project, I will link below in the comment section the presentation video for that. So aerospace is my focus, so I wanted a project that's in that general area. And through research and internships and projects, I'd already done a little bit of work on rovers and rockets and stuff. So I wanted to do something that was new for me so I could get some more dynamics and some more systems in the experience belt. So also control systems applicability was important, as well as cost and availability of components and the potential to develop further. So with that, UAV was decided on, and I considered a fixed wing UAV, but the linear distance needed for takeoff and landing was something that I would have had a harder time accessing here downtown Montreal, so a quadcopter, or the traditional drone that you think of, was chosen. So from there, I started doing some scoping of the system and trying to define what I wanted as functionality. And I started with big ideas like potentially computer vision, landing site detection, and eventually with the semester workload and time constraints, I pared down to two main things, which one was stability and auto hovering. So essentially, once it was in the air, it kept itself relatively level. And the other one is altitude control. So after it lifts off, when it's stable, it doesn't vary too much in height either. So to realize that, I used a PID control algorithm that took data from the sensor that I had, an IMU, or inertial measurement unit, which essentially the raw data was gyroscope data and accelerometer data. And then for the height, I used an ultrasonic distance sensor. And as I mentioned, component availability was important, but so was compatibility. The UAV market is a pretty big one, and so getting the components such as motors and propellers that worked with each other was something that was daunting at first. But after reading some different blogs, specifically one from Juke Brooking, a wizard at UAV stuff from the Netherlands, that kind of gave me a build kit, so to speak, where there's some predefined components that were guaranteed to work with each other. And with that, I was able to focus more on the systems and the circuits and the programming, which was the goal of the project. So here is the overall system flowchart, and it's a little bit zoomed out because there's a lot of pieces, so I split it into two different sections. Section 1 is the first phase of the system, which is startup and calibration. And essentially there's getting the inputs all set up, so the gyroscope data coming in, the accelerometer data coming in, and the distance data coming in, all analog. And output, we have the pulses, the ESC control pulses, electronic speed controller, which in turn drives the motor at specified RPM depending on their pulse width. And then lastly, the LED, so one digital signal out. And then the first thing to do is set up the communication between the IMU and the controller board. After that, the gyro is calibrated because in fabricating the sensor, there's a little bit of offset when all of the different values. So 2000 measurements were taken and averaged, and then the offset for each axis was adjusted appropriately. And then the next phase was the calibration of each of the ESCs, because those needed to be calibrated before each flight, and blinking of the LED to make sure it was understood that that's the phase that the system was in. I didn't actually use a transmitter and receiver controller because after doing some research, that alone would have been almost more expensive than the rest of the components of the kit. So that was one reason I didn't use it, and the second reason was because the goal for the system was to be fairly autonomous anyway, so I figured that that would be an extra challenge. After all of the calibration, there's a LED turns off right before flight, so everyone knows that it's about to take off and can have adequate clearance. Then the initial height reading, or the ground level measurement, is taken, and the system phase variable is set to phase 2, which is the flight sequence. So the flight sequence flowchart is here, and essentially there's two things that I wanted to have as as criteria for the stop of the takeoff and increasing in altitude sequence and starting the descent, which was one, either the maximum height pre-programmed was reached, or the maximum throttle that was pre-programmed was reached. So you see these decision points, kind of a cascaded if-else style, where was it in the first time range? Yes, then it starts the propellers at low, and then the next time range, it's the propellers are a little faster, and so on until you reach the maximum throttle, and then it starts to work itself back down. So the propeller speed slowly decreases, and the UAV descends. Or the height is red, and it's noted that the maximum altitude set point is reached, and that actually jumps the loop counter forward to right before the descent cycle. So with that, after that fixed time period is over, then it goes into the descent cycle and the propeller speed starts decreasing. And you see here there's the stability control black box, so to speak. And again, because this is both embedded and control systems project, the control system there is discussed further in the control systems presentation. So after the set time has been reached, then it goes and changes the system phase variable to 3, which is the ground sequence, and it essentially goes into an infinite loop checking if it's in phase 3, which yes, it always will be, because there's nothing that will change it. And then it blinks the LED until someone goes and resets it, or disconnects the batteries, reconnects the batteries, etc. So here's the schematic. We have the microcontroller, the Arduino Mega 2560. We have the IMU, which the MPU 6050 was the actual sensor in the GY521 breakout board. We have the ultrasonic distance sensor. We have the ESCs, which take power in from the battery. One of them actually supplies the Arduino with the power to run the board, and it also sends the signals to the motors. And lastly, we have the LED, of course, for system phase identification. And the last couple of things is we have breadboards that we used for the signal wires, of course, and then some hardware such as the propellers, the airframe, and some securing methods like zip ties and rubber bands. Now, for the systems interfacing and programming and communication protocol, each sensor used a different type of signal. So the IMU used I2C, which only uses 2 wires, as shown here, the SDA and the SCL wire, but it passes bits back and forth. So that had to be set up using the wire library. The control signals for the ESCs, luckily enough, are the same as for the servo. Same signal range, so that was pretty easy, just use the servo library there. The ultrasonic distance sensor, again, pretty straightforward, trigger echo to signal wires, and then the LED and power signals, which are pretty straightforward. Now, as seen above in the schematic, not a huge number of hardware components, so most of the functionality of the system was done programmatically. And so to make that as efficient as possible, a lot of good programming methodologies were used, such as using as many functions as possible to keep that light and streamlined. Unit testing, so make sure one chunk of code, one system is working before trying to integrate it into further things or trying to work on other stuff. That made the development at least kind of a linear progression instead of some things going fast, some things going slow. A lot of printing was done to the serial monitor to make sure the debugging and calibration was moving as desired. And then lastly, everything needs to run at 4 milliseconds or less, because the ESC signals actually were a signal rate of 250 hertz. So what that means is that for this whole system, this whole loop, each time it made the measurement and made the correction, it had to fit within 4 milliseconds. So that's also why the measurement for the height was only taken once every second, because that library is very slow. The ultrasonic library is slow, so any more than that and it would mess with the rest of the system. So here we have some of the integration steps. The first big one was getting all of the hardware put together and integrated. So here we see the airframe, the motors, propellers, ESCs in the corner. We have the solder made to the power distribution board for each of the ESCs. because you don't want to lose power to one of them during flight, so those needed to be soldered. And then we have the verification that those solders were well made, because the battery voltage was coming through to each one of those different ESCs. And because the microcontroller was actually powered by the ESCs, we wanted to make sure that that signal coming in was also something that was compatible and wouldn't have any danger to the board. And then here we have the oscilloscope, excuse me, showing the signal actually being sent to the ESCs, the PWM signal, and at 500 microseconds time division, we can see that the 1100 microsecond signal is exactly as we were expecting. So after that was all set up, the second big phase was the IMU and getting that calibrated, having it communicate with the Arduino and getting usable data. You can see a little code snippet here, so it's a lot of bit shifting and getting one bit, getting the other bit at the end of a certain range of values, and then, adding them, subtracting them. So it was not straightforward, and even after a lot of play, getting this readable data, it's still relatively unintelligible, right? So what is this negative 3000 value? So a lot of reading, a lot of research was done in this phase, and probably the phase that took the most time of the whole project. And so eventually, after that was all set up, some functions and just some data manipulation was done to get the values as stable and as smooth and clean as possible. So there was a couple of filters that were done. There was some coupling and a couple other things that were done programmatically to get the sensor values to be as true and accurate as possible. And lastly, the PID gain and control. The controller was set up in terms of its function, and again, it's a programmatically designed PID controller, so it's just a function that would calculate the values needed and then send it back. And that was actually manually configured afterwards, after everything was all integrated, so the circuit was verified to be functioning appropriately, all of the sensors were connected to make sure all of the data was being passed as it should. Then it was all mounted, and after it was mounted, another round of calibration to make sure that true level, as shown in this picture, was established for the accelerometer sensor, as well as the rest of the sensors balanced to the fully integrated system. So now we'll jump over to YouTube, so I can go into full screen and we'll watch some of the videos of the setup, integration, and debugging. So this is the connecting the propellers for the first time, the motors for the first time, getting that all functioning. So that was working as desired. Okay. I'm actually just going to leave this here because I'm talking in the other video, but you see this is the integration of the software, the first full version of the software to the controller, and it's uploaded, so that means it's about to start its regular cycle. Calibrating, it prints out, which means it's calibrating the gyro. It's taking those 2000 measurements to adjust the offset. Then it starts blinking, which means it's moved into the calibration phase for the ESCs, which I tried to get all of them to calibrate at the same time, but because I wasn't using a transmitter, that was not something that was possible, so I had to calibrate one at a time. But because there was no transmitter and it was completely autonomous of the system, that was actually a good thing because it gave plenty of time to make sure there was adequate clearance before it started its flight sequence. You should actually be able to hear. Oh, so the light went off. That means it's about to start its flight sequence. Yeah. So we'll listen to the beeps at another time. But you see it's reading the roll and the pitch data appropriately, which means that the sensor was still functioning as expected. Everything was functioning as expected. We have also a little demo that I show up here where the distance sensor takes that first reading of the initial ground height, and I used inches instead of centimeters because inches is a wider measurement, so a little bit of fluctuation in its height wouldn't change that measurement, and that way once it reached it, it had a little bit of margin for play, and that was a good thing for the system. So here I'm just going to unmute that a little bit. So here, this was after everything was all integrated, and this was before the tuning of the PID, so just the P gain. And with that, you can hear that it is doing its adjustment. So as I move it, you can hear the propellers trying to compensate for the move or the shift in the body position that I did. So this was after all of the PID gain values had been calibrated, and you see my hand there, and this is actually not holding the UAV, it's more just like a guide. My fingers are just very, very close to it. So this is all flying, doing its own control, and essentially I just, as you see, I'm inside testing just to make sure the gain values were right. And my hand was there just to make sure there wasn't any overcorrection and it got away from me. But essentially, it was doing its full correcting algorithm on its own. Here I'm going to go just a little bit faster through because this section of flight test is more relevant to the control systems part of the project, but I still want to show a sequence. So with the unmute, hopefully you can hear the ESCs calibrating. You can see the little jitter in the propeller as they finish their calibration. The LED is blinking, which means it's in calibration mode. And I'll just leave this unmuted so you can hear the difference in speed. That's the first speed. Then the propellers go faster, and the propellers keep increasing in speed in steps until they get to the takeoff speed. There it is, and so I slowed the video down just so you can see a little bit of the correction algorithm in action, and you see that it's actually fairly stable. The one issue is that the trim is off, so it's drifting forward. So that was tried to be corrected. So I went back and programmed the trim back again because there's the little calibration that's programmed into the accelerometer. And now it was too far to the right, so I drifted to the right. But again, in the slow-mo, you see that there is active corrections being made to the position, and so that the stability algorithm is running. And unfortunately, the more I ran it, the more I bumped into things, and the propellers got dinged up, which meant the stability possible went down. The balance of the propellers was less, and so overall the system became less and less stable. Just one of the things in terms of testing, I couldn't find the time to get out to some of the open spaces here, and I couldn't test it in the city parks. So here's a test flight that, although it seems unstable in the regular speed, you actually see, I think, a very good demonstration of the stability algorithm functioning. And it hits its leg here, which sends it off. But as it goes back, I'll describe that, look, so it's drifting, but it's correcting its drift, and it's a little unstable, but it corrects itself. So one more time, it takes off, it gets a little unstable, and there's the peak controller correcting itself, and then it starts to drift to the right, and so the eye controller kicks in and starts to try and correct that drift back to the left, but ultimately it's not high enough to have a really clean flight pattern, and because of the enclosed space limitations, I couldn't, the higher it up, the further it can travel if it drifts, so that was just not feasible for this testing. So with that, the focus shifted for a high, stable flight to a full flight sequence where it raised its prop speed until it did a little bit of correction and then landed back down, which was what was just shown there. All right, let's just jump back over here to this presentation. So, a couple lessons and takeaways. Theory does not equal function. It sounds straightforward, but moving things from a software or theoretical realm into a physical system always is not as straightforward as you would imagine. And with that comes the variability. Some things could take a small amount of time to integrate, some things a much larger amount of time to integrate, and you're not ever really sure which ones will take what. So building in adequate time for each of those testing phases is important. For this project specifically, I had buy extra propellers or guards. So with my spatial restraints in testing, my little small backyard area, it just wasn't really enough space, and that damage to the propellers really decreased my stability, and so continual testing was just out of the question. But if I had more propellers, then I could potentially have tested more, or if I was able to have access to a larger testing space, that would have been good as well. One thing with building on a breadboard is that although it's nice and it's modular and you can rebuild something afterwards, the signal connection quality is a little less. So I found sometimes I would be developing something, put it away for the night, and I literally wouldn't touch it, but I would bring it back on the test bench and it would have changed by the next time I tried to work on it. So that, although has the benefit of being modular, the decrease in predictability in terms of its signals was not as ideal. One thing I learned in this project is that you can't reconnect an Arduino without it restarting the whole program. So I tried at one point to get flight data. I set up variables to hold the flight data, and then I was going to reconnect it so I could do some data-driven design, import the flight data, and then improve the controller that way. Turns out it just restarted my program, and because the battery was still connected, it jumped over the calibration phase and started the propellers, and it just flipped over. So nothing seriously damaged, but at the same time, that leads me to the next point, which is safety first. Anything that has a high movement potential, secure it down. And throughout the whole rest of the development phase, I never had any issues with that because each step was very methodically done in terms of assuring that there was always a failsafe. But that was just a variable that I hadn't encountered before, which was the replugging in the controller board. And for my other microcontrollers, that had never been an issue. So it's just something to know about developing on an Arduino that is different. And the last couple things is definitely learning a little bit more about the control system would have probably made it better, and I could have increased its performance. And last thing is, don't forget idiot checks. I had done a lot of development and tuning before I realized that I had actually flipped my z-axis, and it actually was coming in as flipped right from the sensor. So the system was continually rotating, and I couldn't figure out why, and so I had to trace it back all the way. It was literally the first value coming back from the sensor that I forgot to multiply by -1. So it's simple stuff, but if things aren't working, definitely something worth checking. And with that, that concludes the presentation of the embedded systems part of this project. Again, if you're interested in learning more about the control systems aspect, I have the link below in the comments, and I hope you guys have enjoyed the presentation.